Greetings once again and welcome to another SETMind edition. In this edition, we are looking at a very interesting topic called Fourier Series. And what we hope to achieve with this lesson is to give a background, the important concepts, and a few questions thereafter if time permits. So the first thing which we need to understand is the foundation of what is happening with Fourier Series and what kind of questions you are going to be given. So first we'll consider a function f of x. And for the most part, what you should note is that this function, for the problems you will encounter, it will obviously be given. And what we will be required to do is to determine the Fourier series of f of x. And how the Fourier series of this function of ours f of x will be, or how we express it, is simply f of x equals half of a0. We'll quickly see what those means. And then we have the sum to infinity from n is 1. And what we are summing is the following. We have an multiplied by cos of 2 pi nx divided by t, where t is the period, and then plus bn multiplied by sine of 2n pi, and then multiplied by x divided by t, where t is the period. So as mentioned, in this expression, our t is the period. Specifically, it is the period of f of x. And for the most part, what we are going to be working with is, for our Fourier series, we are going to work with periodic functions. So meaning whatever f of x that we will be given, it will be a function that is periodic. What does that mean? A periodic function is a function which, if we take as an example f of x and then we add t, this gives us the same value as f of x. That is what we will call a periodic function. Now we need to start wondering, obviously, with the definition of our Fourier series above, what is a0? And how we find a0 is going to be very easy. Our a0 will simply be 2 over t, which is our period, and then the integral of, but maybe let's mention that, well, t is our period, we did mention, it will be the integral from negative t over 2 to t over 2. And what we are integrating is whatever function that we are trying to find the Fourier series of. And this will be with respect to x. That is our a0. Now let's go to our an. How do we find our an? It is in a similar form. It will be 2 over t and then the integral of negative 2t over 2 to positive t over 2. And what we are integrating is f of x multiplied by cos of 2 pi nx over t, and then this is integrated with respect to x. Then let's have a look at bn, which we need for us to determine the Fourier series of f of x. So our bn will also be 2 over t. Then the integral from negative t over 2 to t over 2, what we are integrating is f of x multiplied by sine of 2 pi nx divided by t. And this is integrated with respect to x. So this is how we are going to find our bn. But before we go and start dealing with problems, there's a couple of notes that we need to have a look at. So the first set of notes or things that we need to remember is the idea of even and odd functions. So first, what we are going to do is, as you remember, there's conditions for a function to be even, there's conditions for a function to be odd, and there's also conditions for a function to be neither. So first, what we are going to be looking at is conditions that need to be met for an odd function. So the condition that we need to make sure that is met for us to classify a function as an odd function is this condition here. F of minus x must always be the same as f of negative x. This condition here is very important. And the reason why we are learning about even and odd functions is that they will make our life easy when we start finding the Fourier series. And you will see how later. So an odd function needs to satisfy this equation. It must be met at all costs. So in order for us to start having an appreciation of what we mean here, we'll start looking at a few examples. So let's have a look at example 1. For example number 1, we have a function which is f of x equals x. And the question is that, is this function odd? So what we are going to do is we are going to go wherever we see x, we put in minus x. So meaning wherever there was x, we put in minus x. And if you observe carefully, you will see that that x there is f of x. So this is the same as negative f of x. So we can see that our f of minus x is the same as negative f of x. So we can safely conclude that our function f of x, which is x, is odd. Okay, that is the test we are going to use when we deal with these problems. Let's have a look at another example. Let's call it example 2. And for example 2, the function which we are given is f of x equals x cubed. So if you look carefully, we are going to do f of negative x, which means we'll have negative x all cubed, which will end up giving us negative x squared cubed. And if you observe carefully, that x cubed is our f of x. So even on this case, what we have found is that f of negative x is the same as negative f of x. So we can conclude that our f of x is odd. So it is odd. Let's go and have a look at another example. Let's call it example 3. And for example 3, let's consider f of x to be equal to sine of 3x. So what we are going to do is to test what is our f of negative x. So meaning wherever we see our x, we are going to put negative x. And if you remember from your high school, sine of a negative angle becomes negative sine of the same but positive angle, which means we'll have negative sine of 3x. And when you look carefully, this looks like our f of x. So which means we ended up having negative f of x. So we now have the condition negative f of x equals f of negative x equals negative f of x. So we can now conclude that our f of x, which is sine of 3x, is odd. So it is an odd function. Okay. And there's many other examples that you can look into. Let's have a look at example 4 and see if this is an odd function or not. So let's have a look at f of x equals x squared. So what we are going to do is wherever we see x, we are going to put negative x. So we'll have negative x all squared. And when we square this, we get x squared. And x squared, we remember, this is the same as f of x. So what we see is that our f of minus x is equal to f of x and not negative f of x, which is what we expect when we are dealing with odd functions. So this means we can conclude that our f of x equals x squared is not an odd function because it doesn't meet the conditions we require for odd functions. Okay, so that is about what you need to understand with odd functions. So in summary, as mentioned, for odd functions, what we require is this condition to be met. We just need to make sure that our f of minus x is the same as negative f of x. Okay, now next let's dive into even functions. So we've done odd, we now need to deal with even functions. So first we need to establish what is the condition that needs to be met for a function to be classified as an even function. So let's have a look at the condition that we need to make sure that we do meet for a function to be considered even. That condition is whenever we are doing f of negative x, we should get the same answer as f of x. That is the condition that we are going to use to test if a function is even or not. So let's go and have a look at a few examples. So we'll have a look at example 5. And the question we are asking ourselves is this even? Okay. And the function which we are given is f of x equals 3x squared plus 4 as an example. So what I'm going to do is go and do f of negative x. So meaning wherever I see x, we go and put negative x, we square that, we put in a 4. When we square negative x, by now you should know we just get x squared, then plus 4. And if you observe that, that is just as good as f of x. So as you can see, our f of negative x is the same as f of x. So what is our conclusion? Our conclusion is that f of x, which is 3x squared plus 4, is even. It is an even function. Let's have a look at another example. We'll call it example 6. And the question still stands, is this even? Is it an even function? And the function that we are going to be looking at is f of x equals 2 cos of x plus 3. So let's go ahead and do f of minus x, which will be 2 cos of negative x plus 3. By now, you should know that cos of negative an angle is the same as cos of the same but positive angle. This is just grade 11 and 12 stuff. So this is cos of x plus 3. And if you observe carefully, this is just the same as our f of x. So we can clearly see that f of negative x is the same as f of x. So we can safely conclude that our f of x equals 2 cos of x plus 3 is even. Okay, let's have a look at the last example. Let's call it example 7. In fact, let's go to functions which are neither odd or even. So remember, you have even functions, you have odd ones, but it so happens that at times you have a function that is not even, a function that is not odd. So that is the question which we need to answer. And that question is, so what happens if we don't meet the conditions? So what if these two conditions are not met? So what if f of negative x is not equal to negative f of x, meaning not odd? And what if f of negative x is also not equal to f of x? So what this one means here is not odd. And what this one means here is that our function will not be even, so not even. So in this case, we will safely say that our f of x is not even and not odd. So then f of x is not even and not odd. So it happens. If we can't satisfy both conditions, it means our function is not even and also not odd. Let's go and have a look at an example that will show us this in application. Let's consider that as example 7. So on example 7, we are given a function f of x, which is x squared minus x minus 6. So what we do is we are going to do f of minus x. This is our test, as we always do. So we'll have minus x all squared minus x minus 6. So if you look carefully, we end up having x squared plus x minus 6. And if you observe carefully, this doesn't look like we multiplied the original function by a negative. So this is not equal. So meaning that what we have here is not equal to negative f of x. That is obvious. And then at the same time, when we look carefully, this function that we now have is also not equal the original function because of this plus here. It is also not equal to f of x. So as you can see, we can clearly see that our f of minus x is not equal to negative f of x, and our f of negative x is also not equal to f of x. So we can safely conclude that our f of x given by x squared minus x minus 6 is not even and not odd. And obviously the question which you start asking yourself is, why is this so important? The reason why we need to do these odd and even functions, it is because it helps us to simplify our problem when we are doing Fourier transform. So you will see that some components we will not need to do if a function is even or odd. So let's make a note of that. That is why we're doing all of this. So to illustrate the note which I've made here, let's go to the next page and start having a look at this. So remember that originally we defined our Fourier transform, our Fourier series. So we defined the Fourier series for f of x. And how we defined it was as follows. So I'll go and put it up here. So we defined our Fourier series as follows. That was originally. But now, after having understood even and odd functions, we will actually work out a different form. And this is where the idea of even and odd comes in. So we are going to say we are going to be looking at our Fourier series when f of x is even. So how does this equation change when f of x is even? Well, what is very important to note is that if f of x is even, there's a couple of things we don't need to do. We do not need to calculate Bn. So if you do calculate Bn, you will actually find out that it will amount to 0. So Bn is the component that will be multiplying our sign. Okay? And we did define what these are. And then secondly, what we need to note is that there's two things that we need. We need our A0 and we also need our AN. This is for when our Fourier series is, or when our f of x is even. Okay? And how we calculate A0 and AN, this does not change. It remains as it was before. Now with this in mind, let's go and have a look at how is the difference. What happens when we are looking for the Fourier series when our f of x is odd? So when we are looking for this Fourier series, when f of x is odd, we have a couple of things that we need to note. And the first one is that we do not need to calculate our an. So if you do attempt to calculate an, you will realize that you actually get 0. And secondly, what we need to note is that our a0 will actually be 0. So for the most part, there's no need to worry about this. And now we need to get into exactly what we need. So whenever our function is odd, we definitely need to calculate our Pn. Okay, so how do the equations change? So let me quickly write the expression that we are going to use whenever our function f of x is even. So the expression we're going to use will be a0. In fact, it will be half of a0. So we'll have half of a0 and then plus our sum from n is 1 up to infinity. And remember, the only part that actually disappears here is the Pn. So which means all what we'll be having is the an multiplying cos of 2n pi x divided by t. Okay, that is what we will use. And then when our f of x is odd, our f of x or our Fourier series, when we find it, will simply be the summation from n is 1 up to infinity, and we'll have bn and then sine of 2n pi x divided by t. So this is how we are going to define our Fourier series when our function is odd. And then the top one, let's say, or maybe now let's include when our function, what happens when our function is not odd and also not even. So when our function is not odd or not even, we will use the original definition. So I'll copy that original definition. That is how we are going to determine our Fourier series. And when our function is not odd and not even, we actually need everything. So it means we need to go and calculate our a0. We also need to go and calculate our an. We also need to calculate our bn. So once our function is neither odd or even, we need to look at the totality or the original expression or definition of our Fourier series. Next, before we even start looking at the problems, I would like to bring to our attention a couple of important notes which are going to be relevant as we work through problems, and you'll see that later. So I'll call those important notes. So the first note that I need you to be aware of, and this goes back to what you might have done when you were doing algebra earlier, which is that cos of n pi, so we'll consider n to have integer values. Okay, so cos of n pi is the same as -1 to the power of n. So if you go and plot the cos graph, you will see that it behaves exactly this way. Then what I need you to be aware of is that sine of n times pi is just always going to give you 0. So meaning when we work our problem out, wherever we see sine of n pi, we'll always put 0. And then, as you might be aware, cos of -n pi, this really doesn't change anything. This just becomes -1 to the power of n. So this is very important for you to keep in mind. Another aspect that I need you to keep in mind is integration by parts, because we will need it as part of our problem solving. So if you remember how we find our an and bn, you are multiplying two functions that are dependent on x. And with integration by parts, what you have is the integral of u dv equals u times v minus the integral of v du. So this would be doing it by integration. But however, for the most part, there's a table that you can also use for you to do your differentiation or your integration. And on this table, what you do is you have two sides. On one side, what you do is you derive, meaning differentiate. And on one side, what you do is you integrate. So you will take your u, and your u would be a polynomial for this to work. You would need your u such that when you derive more, you will eventually get to 0. So u would typically be a polynomial, of which when you derive, it will eventually approach 0. So you'll have your u here, and then you'll have your dv. And then you start doing your derivative. So you derive once, meaning you integrate there. Then you derive twice, meaning now you have the integral there, and you derive 3 times. Now you have the second integral on v, and this carries on and on and on and on up until you eventually get to have a 0. Okay, and then you would be having whatever the nth integral of v would be. Okay, and once you get this, you are as good as done, because all what you do is as you differentiate, you just change the sign. We put a plus minus, then plus minus, and so on up until we get to the 0. And what you do, you just multiply across like that, and so on, and so on, up until we get to 0 times that. So that is what you get. And then all what you do now is you just sum the answer which you find. So our integral u dv would now be, if you look carefully, u times v, and then minus our u dash times the integral of v. And then if you observe carefully, our second derivative, and then our second integral of v, and then minus our third derivative, and then you would be having your third integral of v, and so on. This will carry on up until you eventually get the nth derivative, which will make our u to be 0. So this will be up until we get the nth derivative of u to be 0. Okay, and that is where you stop. So this is going to be very important as part of your work which you need to, or as part of your tools which you are going to use when you do Fourier series. So another concept I want to introduce you to is there's an idea of full range and half range. So that is what we are going to look at here. We are going to look at full versus half range. And when we are speaking of this range here, mostly we will be speaking in terms of the period. So the period is what is mostly affected. Okay, so let's go and have a look at full range. So whenever we are talking about full range, let's start by looking at our definition. So if we have f of x plus t giving us f of x like this, what this means is we have a period of t, standard. But then what we can have with full range is a function. We can have our f of x defined between negative t over 2 to t over 2. So if you think of this carefully, from t over 2 to, from negative t over 2 to t over 2, that is a full period. So this will be full range, because from that to that, we move, or we have a period of t in between. And what that means for our functions is that we'll have our Fourier series defined as follows. So if our Fourier series is defined as such, the change that we will face will be when we are determining an. So your an, when we have full range, will be your 2 over t, and then we'll have the integral from t over 2, negative t over 2, and we'll have f of x, and this will be multiplied by cos of 2n pi x over t and dx. There's something that I'll need you to note. And let's go to Bn. For Bn, we'll have something similar, where we'll have our 2 over t, and then you'll have your integral from t over 2, negative t over 2, and you'll have your function f of x, and this will be multiplied by sine of 2n pi x over t dx. Okay? And what I need you to note is that whenever we are dealing with our full range, we'll be moving from negative t over 2 to positive t over 2. So I just need you to note those, okay? And then same goes for your a0, that will be t 2 over t, and then from negative t over 2 to t over 2, and we are just integrating f of x. So this is full range. Now let's go to half range, and we'll need to note the difference because it is very important. Let's have a look at our half range. So for our half range, it changes how we find our an and our bn and a0. Okay, so let's put that. So for half range, what do we mean? What we mean is that our function will be defined. Let's say f of x, it will be equal to something. Then when they define our period, they will use, let's say, from 0 and then greater than, let's say, x, and then 2 pi to t over 2. While with the other one, the previous one, what we had is f of x equals something, then our x will be between t over 2 and negative t over 2. So with this one, here's the difference. It is from 0. And that changes our approach to how we find our a0. So our a0 changes. Instead of now having a 2, we will now have a 4. So we now have a 4 over t. It's very important that you note. And then we start from 0 up to t over 2. And you'll be integrating f of x dx. So now I need you to note this here. We have changed that. That has become a 4. And this has become a 0. And that remained as it is. It is different from when we have a full range. And same applies to when now we are looking at an. It will be 4 over t instead of having a 2. And then we have the same expression. And once again, if you look carefully, there's the 4, and then the limit, the lower one, is now a 0. So make sure that you look at your problem whenever you are given, is it a full range or I'm looking at a half range problem. So next, let's go and have a look at a problem to better understand what we have been doing here. So if you look at this problem, the easiest thing to spot here is the period. So if you observe carefully, we are given that f of x is the same as f of x plus 2 pi. And we know that it's only the period that could allow you to achieve such. So this means that when we are looking at our problem, we have established that our period is 2 pi. So what might be useful for us to determine first is to just quickly establish, is this function even or odd? So to some of you, it might be obvious that this function will be neither. So if we look at it, it has two parts. So if we do f of minus x, we'll end up having 2 over pi and then multiply it by negative x, and then the other aspect is 2. So if you look at how it is, it will end up being negative 2 over pi times x, but we have a 2. So if you observe carefully, this function is not the same as multiplying the entire function by a negative. So definitely not the same as multiplying everything by a negative, of which how that would look would be negative 2 over pi times x minus 2. So it is not equal to that. At the same time, when we put in the negative, it is not equal the original function, of which the original function would remain unchanged. So it would remain as 2 over pi times x and then 2. So we have a change here. That does not match any of the two forms here. So as you can see, we can clearly see that our f of x is not even and not odd. So what that means for us is that we need to go and calculate our a0. We need it. We also need our an. We also need our bn. So all of these need to be calculated. So the easiest one is, let's go and find our a0. So for our a0, if you look at our function here, it is split in a very interesting way. We are starting from 0 to pi, and then from pi to pi over 2, which is a 2 pi period. So what we are going to do is to compute this, but there's a couple of things that we need to note here, which is that if you look at how we are given the problem, we are given the problem in two parts. This makes it to be a half range. So if you look carefully from 0 up until pi, when we have a period of 2 pi, this is a half range. Okay, and if you think of it, even this one from pi to 2 pi, that is also half the range. Because remember, the full range should be 2 pi. So we are going to treat this as half range problems. And if you remember, when you are doing your a0, it should be 4 over t. What is our t? Our t, we have established it is 2 pi. So I'm going to integrate. I'm going to use the limits that are there from 0 to pi. And what I'm going to have is our f of x. And our f of x, if you look for this range, it is 2 over pi times x dx. And then I have the second component. Remember, I'll have 4 over 2 pi. The second component is this one, where I need to integrate 2, but that I'm integrating between pi and 2 pi. This is dx. So let's go ahead and integrate that. It should be very easy. We'll have 4. If we cancel, we'll actually have 2 over pi. And then when we integrate this one, we'll just have x squared. So we'll end up having 1 over pi x squared plus c when you do the maths, and this will be between 0 and pi. Let's call that c1. And then plus, we'll end up having 2 over pi. And then when we integrate 2, we'll get 2x plus c, call it c2, and we'll be integrating, or we'll put the limits pi and 2 pi. So we can now go and substitute. So our a0 will be 2 over pi into, when we put in pi, you will see that we'll end up having pi squared there. So we'll end up having pi squared divided by pi. And then when we sub in the 0, it will just be minus 0. And then plus 2 over pi into, we'll sub in our 2 pi, which will end up giving us 4 pi. And then when we do the subtraction, we'll be minusing 2 pi. Okay. So if you observe carefully, you'll see that our A0 will be 2 over pi. This will be multiplied by pi, and then plus 2 over pi. And this will be multiplied by 2 pi. So our final answer will end up being, the pi's will cancel, if you look carefully. So this pi and this pi will cancel, and this pi and this pi will also cancel. So we'll end up getting 6 as our answer. So therefore our A0 is 6. So done with A0, we now need to go to AN and eventually also find BN. So let's start our AN. So our AN will be 4 also, because we are working with half range. So 4 over 2 pi. Then our integral from 0 up to pi, what we are integrating is our 2 over pi times x. Remember, with AN, what we need to do is multiply by the cosine function. So we'll have cos of our n, so we'll have our 2x times n pi, then divided by the period, which is 2 pi, and then dx. So let's go to the next page and add the missing component here. But maybe let me create space here. So we need to add the missing component, which is 4 over 2 pi. And that will be integrated between pi and 2 pi. And the function is valued 2. And we'll multiply by cos of 2x and pi divided by 2 pi dx. So let's go to the next page and simplify this. So if you observe carefully, there's going to be cancellation. So the 2 pi will cancel with that, and the 2 pi will cancel with that. So what we are left with inside there will just be AN equals 2 over pi, the integral of, in our case here, it will just be, I'll leave it as 2 over pi times x. Then it will be cos of nx, then dx plus 2 over pi, the integral of 2 cos of nx dx. And let's put in the limits. And what you need to realize here is that we will actually need to do some integration here. And what I'm going to do, I'm going to use the table that I drew for you, because it will make our life to be easy. So we said on one side we'll derive, and on another one we'll integrate. And what we want to derive, we'll choose as u. So we'll choose the part which is a polynomial. So which means I'll choose 2 over pi times x. And then the other part I want to integrate, which is cos of nx. So when I derive this, I end up getting 2 over pi. And then when I integrate, I get, we get sine of nx. Remember, we are integrating with respect to x. So this will be divided by n. When we derive one more time, we get 0. And then when we integrate, we get negative cos of nx divided by, now if you observe carefully, you should have n squared. And then you can have the next part, but that doesn't matter, because once we get a 0, we stop. And then what is very important now is to put in our signs. So we need to have a plus, a minus, and a plus. And then we multiply in this diagonal direction. So that must multiply that, and that must multiply that. So that becomes our answer for the integral. Then the other one is very straightforward. So for that first part, what we are going to have is 2 over pi. After doing our integral, what we have is 2 over pi times x, and then multiplied by sine of nx. This is divided by n. And then we multiply this one and this one. So negative, negative, it will give us a positive. So we have 2 over pi. And then multiplied by cos of nx divided by n squared. And this we can put C1, and this will be integrated between 0 and pi. Let me take this to the next page. And then this needs to be added to the second part, plus 2 over pi, of which we need to integrate. So when you integrate the cos part there, that should be very easy for you to find. When you integrate the cos part, you should get 2 sine of nx, and then divided by x, and then plus C1. This is between pi and 2 pi. So now what we need to do is to go and substitute these pi's and the zeros and so on and see what we obtain. So we have 2 over pi into, if you look carefully, we'll have 2 times pi and then divided by pi, and then this will be sine of, wherever we see x, we are going to put pi now. So this will be n pi, and this goes back to notes which I wrote for you earlier that are going to be very useful when we start doing our simplification. And then plus 2 over pi, and then we have cos of n pi, and this is divided by n, and we need to subtract and put in 0, so that will be 2 over pi times 0, and then sine of 0 divided by n, and then minus 2 over pi times cos of 0, and then divided by n squared. So that is done with the first part of our integral after subbing in. Now we need to go and deal with the second part, which is 2 over pi into, so we need to go and sub into pi now. So I'll have 2 sine of 2 pi n divided by n, and then minus, we sub in the lower one, we'll have 2 sine of n pi divided by n. So there's a lot of simplification that can be done here. So you should remember that sine of n pi will always give you 0. So even this component will be 0, and sine of 0 will always be 0. That component will always be 0. So we only left with the cosines. So this means our answer is just 2 over pi. Open the bracket. We have 2 over pi multiplied by cos of n pi. And cos of n pi, remember I mentioned it is negative 1 to the power of n. And this is divided by n. And then we have this component now, which we need to subtract, which is minus 2 over pi. And this is multiplied by 1 over n squared. So let me double check and make sure that this is correct. Yep, it looks about correct. I'm just missing a squared and a squared here. So if you observe carefully, this can be simplified such that we end up having 4 when we pull everything out, and we have pi squared and squared, and then open the bracket. What we have inside is negative 1 to the power of n minus 1. This is what we get as our final answer, and this is an. So next, let's go and find bn. But what I'm going to do is to take an and then go and change the sign to the cos to a sine. So we're looking for bn now. So an we are done with. So with bn, the only difference is wherever you see a cos, there's a sine. So let's put our sine. And let's put our sine, and essentially we do exactly the same calculation if you think about it. So it will cancel and simplify to be about the same thing, and we'll also use the table. So let's take our an, make it bn, and then take the cos, make it to be a sine. So we'll have sine and we'll have sine. Okay. So what we need to do next, as we used previously, we need to use that table to deal with that first part, where we'll derive and then integrate here. Okay. So what we are going to derive is 2 over pi times x, and what we are going to integrate is sine of nx. So when we derive, we get 2 over pi. When we integrate our sine, we get negative. So it becomes negative cos nx divided by n. When we differentiate, we get 0. When you further integrate, you just get negative sine nx divided by n squared. Then we just need our signs, a plus, a minus, a plus, and then we go ahead and compute our integral. So this means the first part of the integral will just be 2 over pi, and then we will multiply with that, which will end up being negative 2 over pi times x, and then cos of nx divided by n. And then the second part will be a plus, so we'll have 2 over pi, and then multiplied by sine of nx divided by n squared. And then this is evaluated between 0 and pi. Okay. And then we need to add, obviously, the second part where we integrate that. So that will be very easy. It will be 2 over pi. When we integrate sine, we should get negative cos. So it's negative cos nx divided by n and evaluated between pi and 2 pi. So we can go ahead now and do our substitution. So we'll just plug in the pi, which means we'll have 2 over pi into, so we'll have negative 2 over pi times pi, and then cos of n pi, and then divided by n, and plus 2 over pi, and then sine of n pi divided by n squared. And then we now need to do the 0, so which will be minus minus 2 over pi times 0, and then cos of 0 divided by n, and then we do minus, so that will be 2 over pi sine of 0 divided by n squared. So that is done with the first bracket. Now let's go for the second one, which is plus 2 over pi. Open the bracket. If you observe carefully, we'll put in 2 pi, so I'll have negative 2, and then cos of 2n pi, like that. And there's something I think I might need to go and correct now that I'm looking at this. And this will be divided by n. And then we do the subtraction, which will be a plus, and then we'll have cos of n pi divided by n. Okay, so let's just eliminate what will become zeros. So that will be a 0, that will be a 0, and yeah, other parts will not be a 0. What we should note is that whenever you have a 2 like this, your answer actually becomes 1. So let me go and see what I said when we had cos of 2 pi n. We didn't have it. Okay, right, so let's go. So our answer will be 2 over pi into, so the pi's will obviously cancel here, and we are going to have negative 2 into negative 1 to the power of n divided by n. And then all the other parts become 0, including this one. And then let's go, and then we will have plus 2 over pi into that component will be 1. So which means we'll have -2. And then plus that other component will be 2 into -1 to the power of n. And this is divided by n. And that is also divided by n. Okay. So we can now go ahead and collect this. So if you observe carefully, I can factor out 2 over n such that we have addition of components. So this will add up with this to actually give us 0. Yep, they will add up to give us 0. So that and that will cancel. So meaning the only thing left will be -2 over n, which means our answer will be -4 over n pi. So that is our Bn. So our Bn is -4 over n pi. So we now have our An and our Bn. We can now go ahead and express our function accordingly. So let's go to the next page. I'll pick the Bn and then put it up here. Let's go and fetch the An and all the others. So finally, what we can do is go and find the Fourier series. We all have what we need. We have all what we need. We have our An, our Bn, and our A0. So if we plug everything in, you should see that our f of x will be half of A0, which will end up being 3. And then plus, we can do our sum from n is 1 up to infinity. And if you look at our An, we are given our An, so I'm just going to copy it. Or not given, but we did find it. So that is going to be our An, and it's going to be multiplied by cos. And if you remember, when you put in the period, we end up finding an x like this. Okay, so that becomes what we find. But let's maybe make it bigger. And then just sort out something here. We are supposed to have a pi. And then plus the last part, which is Bn. So this is what we found is our Bn. And our Bn should be multiplied by sine. And our sine will be sine of an x. So this becomes what we find as our answer. And the lecturer would be very happy with us at this point, because we seem to understand what we need to do. So this will be our answer. Your Fourier series expression of that function. However, we are not done. So if we go back and have a look at the question, there's a second element to it, which is that we need to also determine the Fourier series expansion of the functions up to 5 non-zero terms. Okay, so once we need to determine terms, the first thing that we actually need to try and do, or maybe the easiest way, would actually to go and plot this graph, because you will understand what is happening. But we can go and substitute our n values such that we get non-zero terms. But maybe for this problem, let's just go and substitute. So we need 5 terms, so that means we need to sub n values to get eventually up to 5 non-zero terms, to get 5 terms. So how are we going to achieve that? Well, remember, what this summation here says is we are going to infinity. But we don't want to go to infinity. We just want to get our 5 terms. So what that means is I'm going to start by looking at n is 1. So when you look at n is 1, it means we need to go to our series. Wherever we see n, we put in 1. So we'll have f of x, and we'll do it for at least 5 terms such that we don't get any zero values. So we'll have 3 into wherever we see n, we put in 1, if you look. So it means I'm going to have 4 over that pi squared into 1 squared, and then I'm going to have negative 1. If you look carefully, we have open bracket to the power of 1 minus 1, and then this will be multiplying cos of x because we are subbing in n is 1. And then the other term will be minus 4 over 1 times pi, and then sine of x. So that is the term which we end up getting. And then now we can go to n is 2. So yeah, so let's go to n is 2. At n is 2, we'll look at our f of x, and we'll have 3 plus. And before I go to n is 2, there's something I need to rectify. So remember that the a0 is only there at n is 0. So I can keep it in one of the terms, but I shouldn't repeat it. So I'm going to remove it here and then only focus on the part. So I'll have 4 over pi squared. And if you look carefully, our n squared will end up giving us 4. And then open bracket, we'll have negative 1, 2 minus 1. And then we'll have cos of 2x. And then minus 4 over 2 pi. And then we'll have sine of 2x. And we'll eventually add these, okay? So now let's go and have a look at the third term. So we need 4 non-zero terms, or 5. So let's go and have a look at n is 3. So at n is 3, we'll have f of x equals, if you observe carefully, we'll have 3 divided by, we'll have pi squared. 3 squared will be 9 into negative 1 to the power of 3 minus 1, and then cos of 3x, and then minus 4 divided by 3 pi, and then this will be sine of 3x. And then we can carry on, go to the next page, look at n is 4 and n is 5, and then sum what we get. So let's have a look at n is 4 and n is 5. So there we go. That is our n is 5 term. So now what we can do is just give the final answer and then wrap up this problem. So our f of x, I'm quickly going to write it. So the 3 is for n is this one is for a0, and then we'll write a1. So done with that. And what you should note is that this term here is for n is 1, and this one here is for a0, where n is actually 0. Okay, then let's go for the next one. So when we summarize for n is 2, what you will realize is you'll end up having this term here. So this is for n is 2, and then let's go for n is 3. And then this next term here is for n is 3. And then next is the term for n is 4. So it is still adding on this expression. And then lastly, we'll put in the term for n is 5. And that is the last term. And this we found by just doing n equals 5. So it's very important that you make sure that you understand all the steps which were undertaken as part of arriving at the final solution. So we had our Fourier series here, and then they wanted us to go and extend and find the next 5 non-zero terms. And remember that with our Fourier series, we have an infinity number of terms. So we have many terms, but they chose to limit us to 5 terms. So that is why we had to go and do all what we did and then sum our answer at the end of the day, because it is summed by that summation sign. And in closing, a skill that might be useful is for you to be able to plot the graph. And plotting the graph is very useful when they require you to evaluate your Fourier series at a certain point. So let's have a look at how our graph will look. So we'll plot the graph. So for our graph, we'll have, if you think carefully, we'll have at pi and also at 2 pi. And then I'll also make it at 3 pi and 4 pi, just to show you what will happen. So here we're at pi, here we're at 2 pi, at 3 pi, and at 4 pi. Okay, so let's go ahead and plot it. So what you should notice that our graph will actually go up. There's a ramp like that, up until it gets to until it corresponds to that pi there. So let's just go up like that. So when we get to pi, if you look at what our graph is, when you put in a pi there, it becomes 2. So it means the y value that I need to put here is supposed to be 2, because at pi it hits exactly that. But then from pi up until it gets to 2 pi, it becomes a different function, which is just the function that is valued at 2. So I need to go and put in a different function that is valued 2, like that. That is how our graph is. And our graph repeats itself again and again after every 2 pi period. What does that mean? It means I should copy the graph, paste it here, and that is how it's going to behave. Okay, and it's going to repeat itself again and again and again with this same trend. So that is how our graph looks. It does repeat itself again and again, as you can see here. And then depending on where they want you to evaluate your graph, you will then need to do the maths. But one thing I need you to understand is that whenever you are trying to evaluate your graph, let's say whenever there's a jump like this, if they say evaluate your graph at 2 pi, if you think carefully, you are starting again, so there's a jump. What we usually do is we'll use the mid value here. So whenever there's a jump, I need you to note that what you are going to do is to take the function value on the right of the jump. Let's say the jump is at A. Take what the value of the function is on the left of the jump, and then you divide by 2. That becomes your value of your Fourier series. Okay, you'll hopefully come across this and you'll understand it, but let's pause here. I hope you understand what we have done so far, and next we'll have a look at another question.